Okay, we will start with, I think all the participants are there. We will start with, I'll share my screen. Give me 1 minute.
Recording in progress.
Yes. Is it visible? Screen is visible to you? Okay, and it is properly visible. Full screen is visible, right? Okay. So, good evening, all of you. We will start with, and yesterday we have gone through the architecture of 8051 in detail. We have seen the architecture of the 8051. While going through architecture of 8051, we have even in detail of RAM of 8051, that also we have seen. Okay, how is the structure of the RAM, how is distributed the RAM, what different bits are there in the RAM, and it is having 128 byte of RAM, whereas 4K of ROM, that is read only memory or program memory, right? After that, looking toward this architecture from program point of view, we have gone through the SFRs, few SFRs of 8051, and out of that, one of the SFR was PSW, that is program status word, right? We have gone through the program status word. What different bits are there in the program status word? Let me go there. Where was it? I think after this we have gone through PSW. This was external memory. Okay, maybe it is in starting. So we have seen PSW in detail. Now, today, in continuation with this, I would like to show you how to access the external memory. Look here, if you remember, I have shown you this diagram. This is our 8051, and in this 8051, internal RAM is of 128 byte and internal program memory EEPROM is of 4 kilobyte. But if more than that memory is required, we can externally connect it, right? So this can be externally connected. How much memory? 64 kilobyte of memory can be externally connected. Similarly, for data also 64 kilobyte of memory can be externally connected. So that much external support we can give to the 8051. Obviously, for more data and more program memory, we, if it is required, that is our requirement. What we can do is we can go for that type of connection. Okay, now going there, going to that external memory connection, I'll go there directly, and then so external memory connection. What is the requirement? How the pin of 8051 has to be connected so that we can access the external memory that we are going to check. So there is one pin, pin number 31. What is it? EA bar means active low EA bar. What EA bar means? It is external access. What we are doing? We want to access the memory externally. If this EA bar is 0, it indicates that code is stored externally. Is it right? What we are storing? ROM, external ROM we are using. So EA bar when it is 0 means pin 31 when it is connected to 0 to the ground. It means that we are storing the part of code or complete code externally. Again, along with that, there is one more pin, PSEN bar and ALE. Even these are used for external ROM. So keep in mind, whenever we are going for accessing of external ROM, what we have to do, EA bar has to be connected to ground. If EA bar is connected to VCC, Means which memory we are using? Program memory, internal program memory we are using. But in case we want the external program memory, it is there connected to our microcontroller and we have to access it. In that case, we have to connect this pin number 3120. It is active low, it is bar, right? EA bar. So active low. So we have to connect it to 0. Other than that, what two important pins are there? One is PSEN bar. Again, this PSEN bar means pin number 29. It is program store enable. What we are doing? Program store enable. And this pin will allow us to connect to external ROM. Okay, so this is one more pin. One more pin is there, which is address latch enable. When you are saying that your program is externally saved, means what? You have to access it. You have to give the address from the external memory at which address your program is there, and that you have to take one by one. So there is address latch enable. This address, it is latching the address for some time so that from that address you can take it. We'll go in detail with this. So keep in mind we have 3 pin to deal with when we are going for external ROM. Okay, and for 80 noise. Okay, okay, okay. Means my voice is not clear. Okay, I give me 1 minute. I'll connect headphones so that noise will not be there. 1 minute. Hello. Uh, am I audible? Okay. Hello. Okay. Okay. I'll share my screen. Okay, so here we are, and I'll put it on full screen. Okay, so I was talking about external memory interfacing, and just what I told here is we have 3 pins are there. 3 important pins are there. One is EA bar, other one is PSEN bar, and ALE. And we have to take care of these 3 pin while connecting to the external ROM memory. I'll go further. Even we talked about PSEN bar and EA bar. This ALE, address latch enable, which is pin number 30. It is what? Address latch enable. It is the important pin for us. It is an output pin and is active high. Okay, remaining two were active low and this one is active high. 8051 port 0 provides both address and data. Is it right? While studying the port, we have seen that from port 0, addresses are also going as well as data is also going. Means when you have to connect externally, obviously at first the address is going and then we have to deal with data, either to take the data in or to give the data out. So the address at that time when we are dealing with that data, at that time address has to be latched somewhere. Okay, and who is giving that signal? This ALE, address latch enable, is giving that signal. ALE pin is used for demultiplexing the address and data by connecting to G pin of this 74LS373 latch. It is the latch. I'll show here in the diagram and you will understand it. Try to understand. This is our 80. Obviously, instead of 51, they are showing here 8031. Okay, it's port 0. This is port 0. What type of data, what this port 0 is handling? It handles address as well as it handles data. What do you mean by AD? It handles address, it handles data. How many bits? 8 bit. Obviously, AD0 to AD7. 8 bits are there. Okay, now when we have to access external program memory, this is the program memory, external program memory, EPROM. That chip is externally connected to this microcontroller, which is equivalent to 8051. It is the lower version of 8051. What is it? 8031. So we are accessing this program memory. For this program memory, how many bit of address is required? 16 bit of address is required because this is of, obviously it is of 16K, so more than 8 bit, almost 16 bits are required for it. So out of it, 8 bits are coming from port 0, remaining bit from port 2. Okay, till this point it is coming from port 2. Port 2, clearly it is giving the address, but this port 1, once it is giving the address and later on what it want, when the address is given, from that address of this ROM we have to fetch the data or we have to fetch the program. Okay, so for that, for some time these address bits are latched here. What they are? Latched here. And that's why for latching it, which pin is required? That latch pin which we were talking about is required. ALE. This is the ALE. Look, this is the ALE connected here. So what ALE is doing? Once the address is given either to the program memory, presently we are talking about program memory, same can happen with the data memory. So we are giving address to the program memory and telling that from this address we are going to fetch the first instruction of the program. Okay, this is continuously connected. This address, these many bits of the address, they are continuously connected. But these below bit, they have to deal with address as well as data. So once that address bits are going, they will be latched here. Okay, they will be latched here, and through this latch they are continuously going, and on at the same time the program is coming from this to my 8031. Do you understood it? How we are fetching the program? We need all the bits of address, so that address we are sending and fetching the program from here. That is how we are accessing external memory connection. And what is playing the important role in external memory connection? This PSEN bar is there. Other than PSEN bar, ALE bar is there. And one more is EA bar. What we have connected to EA bar? To ground, right? PSEN bar, it is going to this program memory. And then the ALE. What we are doing with the ALE? When the signal is coming on ALE. Look here now, ALE. When it is going low, it is active low. So when it is going low, my address port 0, from address, it is shifting to data. What it will carry later on? It will carry the data. Previously, what it was carrying? It was carrying address. Okay. And once the lower bit, lower signal is going on ALE, this will convert, this port 0 will convert to data port. Okay, whereas port 2, it is continuously remaining as address port. Are you getting? This is how external memory access is happening, which is very important part of 8051. Okay, do you understood it? Any question regarding this? Because we are going to the other part now. This is the hardware connection which we are doing there. Is it right? This is the diagram. Obviously, it is of 8031, but same is there for 8051. These are external program memory and this is external data memory. Both we can access by same way. Look, how is the connection? Through the latch. A0 to A7 is connected to EEPROM. And same A0 to A7 is going to RAM also. So that way we can send the address as well as fetch the data or fetch the program from there. Or even if required, depending on reading or writing, either we are reading it or writing it, we can write in RAM also. We can't write in EEPROM, is it right? Because it is read-only memory, but we can write in RAM. Who will decide it? This read bar, write bar. If read bar is 0, if read bar is 0, in our program we are giving read bar 0, active low. So we are reading from this RAM memory. When write bar is 0, we are writing to RAM memory. You can read only from the program memory. You can't write to the program memory. That is how this important part is there. Please check it and give consent to me that you understood it so that we can go for the next part. Means what is important, checking the pins also is very important. Okay, so this way we have completed with the architecture part. In short, we'll go through the pin part. What we are going through is the pin part. I think I am audible clearly. Is it right? Yes, may I continue with my presentation? Okay, there is something in chat. Let me check. Okay. Screen is shared, so I'll start with, we'll go for full screen is shared, right? So this is 8051. This is pin structure or the IC 8051. What type of IC it is? It is DIP, dual inline package, right? It is the dual inline. This one line with the pin, this other line with the pin, and starting from pin number 1 to pin number 40, it is there. And obviously by the pin I will not describe it, but there is port 1 having how many pin? 0 to 7, means 8 pin for port 1 is there. Then the reset is there. Then port 3 is there. This port 3 has other functions also. At first we will check the port 3, 3.0 to 3.7, means total 8 pin of port 3 it is there, and it is having multiplexing. This pin P3.0 is RxD, P3.1 is TxD. This 3.2 and 3, they are two interrupts, which INT0 and INT1. These two interrupts are there. Okay, and they are bar, means they are active low. After that, these two pin P3.4 and 3.5, along with the port pin, they are acting as timer 0 and timer 1 pin. Okay, then P3.6, it is write bar and read bar. We have checked this write bar and read bar in the previous diagram. It was used for accessing external memory. Then external 2 and external 1 is for connecting the crystal oscillator arrangement is connected here. The 8051 running with particular frequency, that oscillator arrangement can be connected here, and then there is ground. Okay, coming from this side, this is port 2, A8, port 2, 2.0 to 2.7. Again, 8 pins for port 2, and what they have? They have address from A8 to A15. Okay, external address, whatever we have to access, it's 8-bit are available here. Then there is PSEN bar, we have checked it for accessing the external memory. Then the pin number 30 is ALE. ALE is active high, as well as oblique. This is used for program bar. Means if this is 1 to pin number 30, if we are connecting 1 means what? VCC, high voltage. Then ALE signal is going for ALE, whereas if it is connected to 0, then program PROG is, that signal is going. Okay, then 31 is EA bar. Again, we have checked this EA bar if you remember, and VPP is there. Similarly, there is port 0. Okay, port 0, it's 7 pin, and what it is multiplex? It is multiplex, not only IO, it is having either the address, we can send address on it, or we can send data also on it. So these are LSB of the address, whereas port 2 is carrying MSB of the address. And again, port 0 is having multiplexing of data. 8-bit of data can be carried or given using this port. So that way, how many ports? 4 ports are there. They have distribution like this. Out of it, port 1 is purely IO port. Remaining port have multiplexing with of different functions. Okay, accordingly the connection is required, and one by one, very short, we will check it. We have checked port 3. They have started from port 3. It is 8-pin port. It can be used as input output, and port 3 has additional function of what? Providing some extremely important signal. Just we have seen port 3. These are very important signal of timer, interrupt, TXD, RXD. This is for serial communication. This is for external memory access. This is for port is completed. So this is port 3. So it is having additional function of providing some very external important signal, right? Along with IO. Then I'll not read now this alternate function of port 3. There only I have shown you what are different alternate functions of port 3. Later on, we have to go in detail of this timer, these interrupts, how they are working, that we have to check in detail. Okay. It's not going. I'm going below 1 minute. Okay. Unit pin function. So that way, pin is completed. I'll share the new part. 1 minute. After pin function, I'll go to timer. Okay, I'll share timer with you, and I'll go to timer. Okay, so now we are going for the new part, and it is timers. What we are trying to understand in 8051 is how are the timers of 8051. I'll put it on the presentation mode. Is it visible to you in presentation mode? Okay, so may I continue? Your voice is not clear. Anyway, I'll continue. So timer we are talking about. In 8051, timer oblique counter operations are available. Okay. Now, at first we have to understand what we mean by timer. We used to set the timer in our mobile. Is it right? Cellular phone. Same timer is available there in your microcontroller. Okay. I am saying it is having timer oblique counter. Counter means for counting the external input which are coming to 8051. So what operations can happen? Either timer or counter. Two timer oblique counter means one timer, one counter, both timer, both counter. That way the application can be set. So is it clear? Timer means internally we are setting the time, and after some time we are asking for some indication. And what do we mean by counter? Counter means on some input pin we are asking for external events, and how many events are happening that we are counting inside. That is called as counter. Do you understood the difference between timer and counter? So, in embedded application, there are many applications where we need precise clock of certain frequency. Is it right? Or count event number of person entering room. For example, they have given it, okay, where we have to generate precise time delay. All these applications are effectively implemented using 8051 timer or counter. Try to understand. If I am going for some application, what happened? It is not moving. Right? The thing is happening like this. Okay. So it is showing when I am not on the presentation mode. I'll keep this. I will work in this mode only. Full screen. Okay. I'll put it. Is it readable? Because if I am going on presentation mode, it is not allowing me to change the slide. Okay. Okay. So we were talking about timer and counter, and what I told you is timer is for internal time setting for generating the delay, whereas counter is for measuring the external events which are happening. Okay. For example, in one classroom I have to do the project of measuring the number of students entering in that classroom. Okay. So what I can do, think of this project. I can put the sensor there. Okay. And if the person is entering, that sensor is giving one pulse. That pulse I am passing to my microcontroller. Okay. And microcontroller, using the counter part of microcontroller, it will go on counting those pulses. So number of pulses coming to me will be equals to number of person entered in the room. So this can be the project. So what I am using in programming, I am using the counter. I am setting the counter and doing that project. Okay. Externally, what will be required? That sensor will be required, which is going to give the pulse when the obstruction is coming. You can search for that type of sensors. Number of sensors are there like that. Is it right? So that is the counter part. Now think of other part. I have to use timer. Particular value of delay I have to generate. Okay. So generating, let it be the delay of 1 second. From the frequency of microcontroller, using the frequency of microcontroller, I can set the timer in such way that it will give me the delay of 1 second. And after 1 second, whatever I have to do, let it be, I have to flash some light after every 1 second. Okay. Some what you can say, some disco lighting is there. Might be you people are knowing that type of lighting, where the lights are flashing after 1 second or less than 1 second. So that much delay I'll be providing with help of timer to that led, and those leds will keep on flashing. So that is the other example. Do you got the difference between timer and counter? That is the difference. Okay. So where we have to generate a precise delay, timer is used, and wherever we have to measure the number of events, in that case counter is used. Okay. Now for example, I have to measure the speed, or the rotation of some wheel. That I can do even with help of counter. Okay. I can again place the led and the receptor which will receive the light of led, that type of sensor arrangement. And the wheel is rotating. When the wheel is rotating, that light at some point, wherever there is hole to that wheel in between, light will be passing. I'll be counting those pulses and the counting will happen. So for number of applications, the thing can happen. Okay. So now, timer, this timer operation it has two ways to generate the delays. So one approach of generating the delay is software based approach. Okay, and it is very flexible approach. Processor is used to count event, generate delay, and processor remain busy for this purpose. Try to understand in your C language you use the delay loop. Okay, what you are doing, you are setting one I and j variable, and then you're putting them in for loop, and using that you are generating the delay. That approach of generating the delay is called as what? Software based approach. Are you getting my point? But during that approach, continuously who is working? Your processor, your microcontroller, or the processor, whoever is the computing unit, it is continuously working. Is it right? Are you getting my point? So there is one software approach for generating the delay. Why I am telling this? Because we are going to use the timer for generating the delay. We have to justify why to use the timer for generating the delay. Okay. So for that, what example I am giving, you can think of software based approach, which is very flexible. You can give the value from you can write down the for loop, you can write nested for loop, you can give the value to them, and those for loop will go on depending on your requirement and the frequency with which your CPU is working. You can calculate the delay, and that way you can generate the delay. But problem of that delay is, what is the problem? Your processor remain busy for this purpose. Okay, that's why we are going for hardware based approach, which is not flexible, and here we are using the timer. Here we are using extra hardware. And what is that extra hardware? The timer register which are there inside my controller or processor, those timer registers is used. Even sometime what can happen? I can use the combined approach of software based delay and hardware based delay. Okay. Try to understand one more important thing about the microcontroller or processor. There is only one ALU. In your microcontroller, how many ALUs? In case of 805, only one ALU is there. And if you are asking to generate, if you are going for generating the delay using software based approach, at that time that ALU you are utilizing again and again. So remaining work which are there for the ALU, they are remaining aside, they have been done later on. Okay, and your ALU is working for the delay. Whereas when you are going for hardware approach, what is happening? Timer is working, ALU is not working. Who is working? Timer is working. So that is a good approach. And what they are saying, if you are combining these two approach, it is even better. Okay, that is how I'm justifying the delay. Oh, sorry, timer based delay. Okay, so in 8051, we have two timer oblique counter. Timer counter 0 means you can say timer 0, counter 0, oblique, either or you can use. Similarly, timer 1, counter 1. So that way, either two timer, two counter, or mix of it are available there. Okay. Now, this timer is used as time delay generator. We have seen it. And this timer is working on which frequency? Clock source. That is internal crystal frequency of 8051. In pin diagram, I have shown you that to external 1 and external 2, what we are connecting externally? The crystal oscillator arrangement we are connecting. And that crystal oscillator is giving clock frequency or clock source to your 8051. So that is called as internal crystal frequency, and using that frequency in timer we are generating the delay. Okay, next thing, event counter. How the counter is working? External input from input pin, maybe any port pin you can use. From there, what is happening? External input is coming to count the number of events on the register, and in that external input, how many changes are happening, that we are going to count. That is how counter or event counter is working. These clock pulses, who is acting as the pulses here? That external input is acting as the pulses. Are you getting my point? In the timer, who is acting as the pulse? Clock source, internal crystal frequency is working. In this case, in case of counter, those input which you are taking from external, whatever you want to count, they are acting as the clock pulse. Okay, and those pulse will be stored in the register. It will go on incrementing the register, and we are going to count it. That is how counter is working. Look, we'll read this. These clock pulses means external pulses coming from IO pin could represent the number of people passing through an entrance or number of wheel rotation or any other relevant event that can be converted to pulses. Okay, this can be the small project for you or small experiment for you. Okay, what to do? Using the counter to count the external pulses or set the timer to generate the delay. Writing the program in C, because generally we are using the C language. Assembly we are not using. So even you can think of using assembly, but assembly is 8051 specific. That's why C is preferred. It is the higher level language. Okay, so this can be the experiment. As you people are learning the microcontroller, it is required at your level. You have to go for program. You have to understand the program and implement the programs either for generating the delay to understand timer or generating the measuring the external pulses to understand the counter. I'll go further. So, a timer count machine cycles and provide a reference time delay. Machine cycle of 8051. Look, one more important thing is timer counts machine cycle. Okay, and machine cycle is what? Machine cycle of 8051 consists of 12 oscillator period. Okay, what I told you. How is the oscillator frequency? It is coming from crystal oscillator. It is getting divided by how much? 12, and that will be equals to machine cycle. And with respect to that machine cycle, your timer is working. Means let it be 12 megahertz is the clock frequency, crystal clock frequency. Okay, so what is the machine cycle frequency? It will be 12 megahertz divided by 12 means 1 megahertz. Are you getting my point? So your timer is working at what frequency? 1 megahertz frequency. That 12 megahertz is getting divided by 12. 12 oscillator period is equals to 1 machine cycle. Okay, so it is getting divided, and that way machine cycle is giving you. Okay, coming to this timer diagram of the timer. So the timer count machine cycle and provide a reference time, set the initial value of register. Okay. Anyway, leave this theory aside. Look this diagram. So at present we are talking about timer 0. Timer 0. So this timer 0, TH0 and TL0, higher 8-bit and lower 8-bit of the timer that we are setting here. Okay, so start the timer and then 805. Look here how the working will happen. A timer count machine cycle and provide a reference time. Set the initial value of register. Okay, in the timer, depending on our requirement, we will set the initial value and then it will go on counting to give us the delay. So start the timer and then 8051 count up. Once we give the pulse to start the timer, from there counting will start. Okay, counting up will happen. Then input from internal system clock, that is machine cycle, is helping to update that timer. When the registers equals to 0 and 8051, set a bit to denote timeout. Don't worry about this thing. We will in detail go about the timer. Similarly, the counter. The counter of 8051 is incremented in response to transition from 1 to 0 at its corresponding external pin, either T0 or T1. Sorry, I say any IO pin, not any IO pin. From where the counter input is coming, it is coming either from pin number T0 or T1. If you remember, this pin was there. Thus, the counter output will be count or a number representing occurrence of 1 and 0 transition and on external pin. how many 1 and 0 transitions are happening either on T0 or T1 depending on what we are internally using. That will be counted. For counting function 8051 take 2 machine cycles or 24 oscillator period. Keep in mind. There in the previous case it was 1 machine cycle and here 2 machine cycles for counting is required to detect 1 to 0 transition at pin T0 or T1. That is how the counter is working. Okay, so look here. On pin number port 3.4, that pin which is also called as T0, what is coming? External events are coming and they will be counted. Okay, they will increment the register of this timer and we will come to know that on the LCD the display will happen how many events are getting inside. That is how the counter is working. We'll go in detail of this now. For programming this counter and timer, we have some internal registers and that registers we will understand here. So both timer 0 and timer 1 are 16-bit wide. How many bit wide registers are there? 16-bit wide registers are there for timer 0 and timer 1. These registers store the time delay as timer or the number of event as counter. Look here, timer 0, its register is TH0 of 8-bit and TL0 again of 8-bit. Okay, timer 0 high byte and timer 0 low byte. This is timer 0 high byte, this is timer 0 low byte. What about timer 1? Again 8-bit and 8-bit. This is timer 1 high byte and timer 1 low byte. In this way 8 and 8 16-bit registers of timer 0 and timer 1 are there. Each 16-bit timer can be accessed as two separate register or low byte and high byte. Separately you can access it. This can be separately accessed. This can be separately accessed. So as we have to go for programming or understanding how to put the values in timer and counter, at first what we have to understand that we have two registers. Which register? Timer 0 register, timer 1 register. What is there in timer 0? Again two register, TH0, TL0. Okay, what is this? 8 high bytes. Sorry, high byte or 8 bit, 8 high bits. TL0, timer 0, low byte. Byte means how many bit? 8 bit. Okay, so how many bit are present here? 8 bit. That way these are there. Each 16-bit timer can be accessed either separately. Look, this way the registers are there. Check it. Do you understand? D8 to D15, 8-bit high bits or 1 byte in total. 8-bit means what? 1 byte. Similarly, the low 8-bit or single low byte of timer 0 and this is of timer 1. Okay. So can you tell me it can run from, in terms of hex we will talk about. Okay, hex means how many bit will make hex? 4 bit. So it can run from 0 0 0 0 in hex, right? 1 0 in hex means 4 0 in binary, is it right? So 0 0 0 0 to maximum where it can go to F F F F. Do you agree? This timer register, it can increment from where it can start from 0 0 0 0 it can start and max it can go up to F F F F. So in this range while happening this, okay, from 0 0 0 0 to 0 0 0 1 0 0 1 0 and so on, that increment whatever is happening in this, for every increment how many how many machine cycles are required? One machine cycle. And what do you mean by one machine cycle? For one increment, one machine cycle will be required. And one machine cycle means 12 clock cycle. Are you getting? So that way we can think of calculating the delay. For example, I'm setting some value in this timer register. I'm setting some value in it. Okay. And I want, so from that value, let it be what I set is 1 for 4-bit 1. Again 1, 1, 1, 1, 1 that I am setting. Now my timer will go on incrementing. It will reach up to what? F, 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 F. In between this 1, 1, 1, 1 to F, 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 whatever is the delay I am getting, that is the delay provided by the timer. So that delay I can set. How I can set? I will put the value in the timer from where it has to start depending on my requirement of delay. That calculation is important. Are you getting? So these are the registers of the timer. Now further, 8051 provides two registers for timer counter control. It's okay for delay there are the register, but along with delay we need the control of that timer counter. So there is one T mod register and other one is T con register. T mod is timer mode control and T con is timer control register. Okay, one is mode control and second one is what? Control register. These are two again important register for timer counter. So what were the first registers? Those were the timer register, these two registers for storing the data which will directly relate with the delay. And what about the other two? For control. Okay, mode control as well as the control register. So T mod and T con. So these many things are there in case of timer. Now this T con timer control register, how it is working, we will check it here. We have timer 0 and timer 1. Is it right? What we have? Timer 0 and timer 1. For this timer 0, we have 2-bit. What? TR0 and TF0. This is the flag bit and this is the timer reset bit. Okay, what 2-bit? TF0 and TR0. This is the flag bit and this is reset bit. For whom? For timer 0. Similarly, for timer 1, we have TR1 and TF1. Same flag bit, reset bit. Means when my timer is full, at that time flag will be high. That your timer reached to what? FFFF. And once it reaches to FFFF, this flag will be high. Okay, and timer will roll down to 0000. Is it right? So from where I'll get the idea that my timer is full? From this flag. I'll use that flag in the program so as to set the further thing in the program. Okay, so TF0 is the flag and this will be reset. Once it is 1, I have to reset it and again start counting. Is it right? Same thing for timer 0, same thing for timer 1. Okay, these remaining 4-bit in timer control registers are related with interrupt. What they are related with? Interrupt. Later on we'll check for them. At present we are looking for timer. So 4 MSB starting from the 7, 6, 5, 4 MSBs. These are related with timer 0, timer 1. So TCON is a SFR. What is it? SFR, 8-bit register of which first 4-bit, that is TF1, TR1, TF0, TR0 are used for timer control. Remaining 4 bits are for interrupt control. Dual purpose part of which used for timer control and other part is used for interrupt control. Very clear. TCON, and at present we are going for timer control. Okay. Now look, what is this TF1? I tried to explain it to you, but then also again we'll read. Timer 1 overflow flag. Okay. It will be set 1. When it will be set 1? After counter roll over from FFFF to 0000H. Means your timer, this is TF1, it is talking about timer 1. When your timer register, timer 1 register, which is timer 1 register, this is timer 1 register. When by incrementing, it reached to what? FFFF, and then once it becomes FFFF, what is the other step? It will roll down to what? 0 0 0 0, and at that position what will happen, your flag bit will be set 1, timer 1 overflow flag bit. This is the overflow flag bit, set 1 after your counter roll over from FFFF 4F to 40H. Once it is full, it will come down to 0. Okay. Then TR1. What is that? Timer 1 run control bit. When I want my timer to start, to enable to start, at that time this TR1 has to be 1. So I will be setting TR1. I'll be checking the flag bit and I'll be setting TR1. Are you getting? In my program, I will be playing with this. I'll be setting it. And what I'm doing with the flag bit, I'm going to check it in my program. Is it overflowing? If yes, then I'm going for the other action. Is it right? So setting the enable, how you can set it? By setting tr1 equals to 1. What I am doing? I am enabling the timer 1. I am asking timer 1 to go on counting. And when tr equals to 0, I am disabling the counting. Are you getting? So it is very crucial thing to be used in program. Then tf0, that is about timer 0, and this is again the flag bit. When this flag bit will be set? When timer 0 overflows. What do you mean by overflow? While counting those 16 bit of my timer, those 16 bit all will be 1 and it will roll down to 0. All are 1 means what? In hex, F, 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 F. 16 1 means what? In the patch of 4 it will be F, 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 F. Is it right? And it roll downs. Once it becomes F, 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 it will roll down to 0 0 0 0, and at that time what will be set? This flag TF0 will be set. It becomes set means what? It becomes 1. So my program will be continuously observing that TF0, and once it become 1, what will happen? I will come to know that counting has been completed. I am going to get the delay which has been set by me. Again the TR0, same working of TR0. I'll be setting that working whenever I want my timer to start. At that time, I am making TR0 equals to 1. When I have to disable the timer, I will be making it 0. Same working as it is here. Do you understood these two important registers or this one, that is timer control register? Just check it once. If you have any question, please ask me. Okay, noise is coming. I think that is the old message and now it is clear. And expecting you understood the timer control register. Okay, so two registers. One is timer control. Previous to it, we have seen the timer registers of 16 bit T0 and T1. T0 is consisting of what? TH0, TL0, and T1 is again consisting of TH1 and TL1. How many bit in total? 8 and 8, that is 16. This is also 16 bit. Is it right? Okay, then we have gone in detail with timer control register, and I told you for this control register how we are dealing in program. We have to check for the status of flag register, whereas according to our requirement, whenever we have to start that timer, we are setting the value of TR bit. Okay, then the next important register in timer is T mod, that is timer mode control. Though we are calling it as T mod, it is timer mode control, controlling the mode of the timer. Now look, how is that timer mode control? It is having MSB, that is most significant bit is get. Then the next one is C oblique T, means counter oblique timer. then M1 and M0, and this is for timer 1. Means we are setting either timer or counter that we are deciding from here, and M1 and M0 it is selecting the mode of the timer. Same thing, same 4 bit for timer 0. So do you got it? Either we can set timer or counter, and the next thing is we are going for mode selection. So tmod is an 8-bit register. Set the usage mode for 2 timer. Okay, set lower 4 bit for timer 0, lower 4 bit, these are for timer 0, and upper 4 bit for timer 1. Look what they are saying. When it is set to 0000, for example, all these 4 bits are 0, means what? We are not using timer 0, and same thing is for timer 1. Okay, now I'll come here. So M0 and M1, these bit they are for mode selection of timer. Same is for timer 0, same is for timer 1. So when it is 00, what is the mode? It is mode 0. What do we mean by mode 0? It is 13-bit timer mode. Okay, when we are putting, let it be, we are going for timer 1, and in timer 1 we are setting 00 here. In that case, what is happening? It becomes a 13-bit timer mode. In total, how many bits are there in our timer? 16 bit. Out of it, how many we are using? According to this mode, we are using 13 bit. Means what? 8 bit from TH. If I am going for timer 1, then it is 8 bit from TH1 and 5 bit from TL1. Are you getting? And if you are going for mode timer 0, in that case TH0 and TL0. 8 plus 5, that is 13. How many bits you are using? 13 bits you are using. Okay, so that is mode 0 of the timer. Then there is mode 1. When the select bit M1 and M0 they are 0 1. In that case, which is the mode? Mode 1 is there. And mode 1 means 16-bit timer mode. All the 8-bit of TH and all the 8-bit of TL we are using for counting. Means we can start from 0000 in hex, and we can go up to what? F F F F. 16 means what? 16 bit will represent maximum all 1, and all 1, what I told you, for all 1 group 4 1 together, and it is giving you F F F F. So from 0000 we can count up to F F F F. Can anyone tell me in 13 bit how much maximum count will be there? How much maximum count will be there in 13 bit? You can write in chat also. Can you try writing it? You have how many bits? 13 bit. So 13 0 to 13 1. Try to find out. And from the lower side, start grouping it in 4. Yes? Can anyone answer? As there are 13 1, and if you start grouping from LSB, it will be 1 F F F. What maximum count can happen in that? It will be 1 F F F. Okay, so I told you about mode 0, I told you about mode 1, and then there is 1 0. When these bits M1 and M0 they become 1 0, it is mode 2. That mode 2 is 8-bit auto reload mode. Okay, what is it? 8-bit auto reload timer oblique counter. Here the THX hold a value which is to be reload into TLX. Whenever we are going for the mode, we'll see it in detail. But from THX, value is getting loaded in TLX. TLX means if it is 0 timer, TH0 and TL0, automatic loading will be there. So that auto loading is happening in case of mode 2. Whereas mode 3, 113 is split timer mode. It is called as split timer mode. So that way Tmod, Tcon and two timer registers we have checked in timer. We talked about this mode. Now what is remaining? This C oblique T. Okay, so it is C T bar. If it is 1, we are going for what? Timer, counter. And if this is 0, it has been set to 0, we are going for timer. Okay, so do you understand? In this bit, if I am writing 1, that means from the timer pin, I am taking the input and that I am counting. It is acting like a counter. And if I am putting 0 here, if I am writing 0 here in the program, means what? I am using the timer mode. Decide whether the timer is used as delay generator or event counter. Okay, C oblique T bar is equals to 0. It is used as timer for delay generation when you are putting 0. Okay, and from that, for that, the clock source for time delay is crystal frequency of 8051. If C oblique T bar is equals to 1, it is used as external event counter. Do you got it? We have seen these three signals. We talked about these three signals. This is for mode selection and this is for selection of timer oblique counter. Okay, last one is remaining. This gate. Gate. Enabling or disabling the counter operation. Gate equals to 0 by software means using TR. Okay, and gate equals to 0 by hardware means using what? INT and TR. Gate equals to 0 by software will be working as a counter, as a timer. And this gate equals to 0 by hardware means we are using it as the counter. Okay, so that way the setting of gate is there. In this way we have checked for all the bit of T mod register. Okay, this is the diagram of timer counter control logic. I'll not go in detail with it. It is not required. Okay. Now we will check for the operation because timer programming is the important part. 1 minute. Give me 1 minute. I'm taking break of 1 minute and coming back. In case you have any difficulty, you can write in. Hello. I took break of 1 minute. That's why I muted myself. 1 minute. I'm coming back. Okay, coming back. Here we are on timer and we'll talk about mode 0 operation of timer. Okay, so look here. This is the timer register. Maybe X means what? TL0 or TL1, whatever we are selecting that timer. So lower bits and higher bit. In case of mode 0, how many bits we are utilizing? 13 bits we are utilizing. Out of it, 5 bit from the TL and 8 bit from TX. Now look, from this side clock is coming. As the clock is incrementing, there will be the change, increment in the timer. So from where the increment will start? From LSB, lowest significant bit. Increment will start, and that increment will go on penetrating towards the highest significant bit, and it will reach maximum up to what? 1 FFF. Why 1 FFF? Because we have 13 bits. So 13 bits maximum will give you 1 FFF. Once that maximum count is reached, my timer register will roll down to what? 0000. Once it roll down to 00, what will happen to this overflow flag which I have shown you there? This flag will be set as 1. From this, what I'll understand? I'll understand that the timer or the delay which I set here has been accomplished. Are you getting? So we'll read here. Mode 0 is 13-bit timer mode. It consists of 8 bit of what? TH and 5 bit of TL. The upper 3 bits of TL should be ignored. Why? Because we are going for just 13 bits. Okay. Instead of 16, we are going for 13. So 3 are ignored. TL is incremented from what? 00 to 1F. And after 1F, TL overflows. Okay, and what it will do? It will increment TH. TH will increment from what? 00 to FF. So in total, what you are getting is 1 FFF. Right? From where we have started? 0000. We reached up to 1 FFF. Okay, this much delay is possible. If I need somewhat lesser delay than that, then what I'll do? I will set the value, some value I will set in this register instead of 0000. From that value I will start, but I'll reach to this maximum count. Okay, are you getting? That counting is required. We will start from some value, reach up to this higher value, and then we will roll back so as to get the required delay by us. Not necessary always we are starting from 0000. We are starting from the value depending on the requirement of delay. And thus, what is important? It is required for us to calculate that delay, whatever is needed by our once for our application, whatever is the delay required. Are you getting my point? Though it runs from 0000 goes up to 1 FFF, according to my requirement, I will set the value, and from that value I will start the counting. Maximum I'll reach here and get the required delay. That's what you have to understand. How mode 1 is different than mode 0? From where we are starting, where we can start from 0000. All 16 bits we are using. And where we can reach max, we can reach to F, 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 F. So obviously more delay we are getting in case of mode 1 compared to mode 0. Are you getting? So mode 1 is 16-bit timer mode. Therefore, it allows value of 0000 to FFFF to be loaded into timer register TH and TL. After starting the timer, it starts to count up. It will go on incrementing, means counting. And what it is counting? This clock which is coming to it, the internal clock, crystal oscillator which is coming to it, getting divided by 12, making the machine cycle, it will go on counting those machine cycles, right? And once all the counting is over, when it reaches to FFFF, it will set the flag. Okay, it count up to FFFF. Then it roll over to 0000 and the flag is set. After the timer reaches its limit and roll over. In order to repeat process, the TH and TL must be reloaded with original value of TF. Are you getting? In the program, what will be required? Once it is roll over, it is roll over to 0000. Again, you have to load the values in TL and TH depending on the requirement of delay. So everything where it is coming in the program, it is coming. Okay, checking the flag, setting the timer, putting the values inside it. That is happening in our program. Okay, so while programming, look what steps are there. If you understood the register, you will understand this thing. Load the tmod value register indicating which timer is to be used. Is it right? What is in tmod? Either timer 0 we are using, timer 1 we are using, that we are loading in tmod. So at first, what we have to program, what we have to load is tmod. After that, load the register TL and TH. We have selected the timer, maybe 0 or 1. Let it be, we have selected timer 0. Then we will load value in which register? TL0, TH0 with initial count. Why we will load it? Because we need the specific delay. For that delay, we will make the calculation and that value we will load to TL and TH. Start the timer. Keep monitoring the flag TF. Is it right? Timer is started. So counting will happen. This TL and TH will go on incrementing. So once it reached to what? FFFF and roll down. What will be set? Flag will be set. So we have to keep monitoring the flag. Once the flag is set to 1, stop the counter. Stop the counter as well as clear this flag so that we can start the next round. Get back to step 2. What is step 2? Load the value in TL and TH. This is how your program will be there. Is it okay? Do you understand what to be written there in the program? In C, you have to write this program. So please, later on after the lecture, check for writing the program because you people are doing the course to understand writing the program. Is it right? Efficiently using the microcontroller. So you must write, you must try writing the program. These are the steps for writing down the program. Do you understood it? Now, what to be loaded in this TL and TH, that we have to calculate. I told you we have to calculate it. So we will check for those calculations. This is the assembly language program which is here. Okay, so anyway, we will go for the calculation, delay calculation. As we are using the timer, how the delay calculations are there. Now, here in hex, we are loading the timer by hex value. Okay, what we are loading there in the timer? Hex values, binary, we can say 10 values in terms of hex, we can read it. So, your timer register, it go maximum up to F, 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 F. Okay, minus this value, some YYXS plus 1, where this YYXS are TH and TL initial value respectively. Okay, and multiplied by what? 1.085 microsecond. From where we got this time? We got this time from the crystal oscillator frequency of our microcontroller. It is approximately 12 megahertz, and 12 megahertz approximately, or say 8051 works at 11.0592 megahertz divided by 12. That is our crystal oscillator frequency. Sorry, that is our machine cycle frequency. What is crystal oscillator frequency? 11.0592. Okay. How many clock, crystal clock is equals to one machine cycle? 12 clock. That's why 11.0592 divided by 12 will give us one frequency. 1 by that frequency will give us the time, and this is that time. Okay, so while going for the delay calculation, what do you have to do? FFFF minus this value, we have to compute this value plus 1, because Along with making the value FF, we have to roll down to 0, 0, 0, 0, right? And that's why this plus 1 is here multiplied by that time that has to be loaded in the what? In the timer register. This is in hex. Same thing in decimal. What do you mean by FFFF? It is 65536 minus this number. Instead of YYXS, they are giving the decimal number which we have to calculate. We are going for that calculation. And this frequency, this time is same. Machine cycle time. This is what? Machine cycle time. Okay. So look, here is written. What is our clock frequency? 11.0592 is the clock frequency. I'm going for that calculation. Look here now. Frequency. What I told you, what is the clock frequency or extal frequency? It is 11.0592. So if this is the clock frequency, what is machine cycle frequency? This frequency extal divided by 12. 12 clock is making one machine cycle. That's why we are dividing by 12, and thus our machine cycle frequency becomes 921.6 kilohertz. If this is the frequency, what is time period of machine cycle? It will be 1 divided by 921.6 kilohertz. It is 1.085 microsecond. Is it right? So these are the basic calculation. After that, let it be my TH0 is B8 and TL0 is 3E. I got it by calculation. So if I am loading what? TH0 by B8 and TL0 by 3E, what will happen from this B8 3E? My counter will count up to, my timer will count up to F, 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 and it roll over. And in between this, whatever is the delay, that will be given to me. Now, we'll go for the calculation of that delay. Problem, yeah, example, we have to check for it. 1 minute. Statement is not available here. 1 minute. How to get it? B830. Just divide the desired. Okay, we'll go for this problem instead of the previous one. So look here, what is happening. So with just keep in mind that what to timing you have to keep in mind. This problem, its problem statement is not presently available with me. Later on, I'll discuss this one also. It is important problem. Okay, I'm not remembering for what delay we have taken this B83E, that I'm not remembering. That's why I'm going for the other problem. If I'm getting it, this problem will be solved. B83E. B83E. Okay, I'll take the other one. You have to keep in mind that our external frequency is how much? 11.0592, and machine cycle frequency is how much? 921.6 kilohertz. Keep in mind. And how much is one machine cycle time? 1.085 microsecond. We have to use it. Okay, so I am going for one problem with frequency of 22 megahertz. Now we are changing the frequency of 20, instead of 11.0592, what frequency we are taking? 22 megahertz. Generate a frequency of 100 kilohertz on pin P2.3. Use timer 1, mode 1. This is the problem. If you want, you can take down this statement. Today we'll just discuss the T mod and Tcon, and later on we'll go for generating that frequency. Look, What is the clock frequency? 22 megahertz. What we are generating? 100 kilohertz. On which pin? P2.3. Okay, and what we are using? Timer 1 in mode 1. So look one by one what we have to do. At first, decide the value of T mod for timer 1 mode 1. So this is your T mod. In it, you are not using timer 0. So what will happen to all 4 bits? What will happen to all 4 bits? 0, 0, 0, 0. Then we are using what? Timer 1. Timer 1 in mode 1. What do you mean by mode 1? Do you remember? Mode 0 is 0, 0. Mode 1 is 0, 1. So M1 and M0 becomes 0, 1. What is mode 1? It is of 16 bit. So 0, 1. These two bit become, this becomes 0, this becomes 1. What this bit will be? As we are using timer, so T bar, this bit becomes 0. And as we are going for software delay, this also becomes 0. So when you are using timer 1 in mode 1, this becomes 0, 0, 0, 1, and this remaining all 0. So look here, 0, 0, 0, 1 and remaining 4, 0. Means what in hex? 0001 means 1 and 0000 means 0. So what in hex you are giving to T mod? T mod become 10H. T mod become 10H. Do you understand this? At first we are setting the T mod. Okay, and what they are asking, they have given us timer 1 mode 1, and according to their requirement we are setting this T mod. Further, now look here, what is the frequency given? 22 megahertz. What we have to generate? 100 kilohertz. What do you mean by 100 kilohertz? 100 kilohertz means the square wave of 100 kilohertz. So how much is the time period of 100 kilohertz wave? 1 divided by 100 kilohertz means 0.01 millisecond. Kilo means what? 10 to the power minus 3 will come there. So 0.01 millisecond. Okay. So that is the period. That is the period of your square wave. So what I want from you people, next time tell me, for generating 100 kilohertz, how much on time and how much off time of that signal will be there. Will it be possible for you? For some time it is on, for some time it is off, and by that way it will give you 100 kilohertz. So how much on time and off time is required for 100 kilohertz? Can anyone try telling me now? If you understand this, then only it is possible that we are programming or you are going for programming. Okay, so T mod we have checked. Please next time find out for generating 100 kilohertz. What you understand by 100 kilohertz, and 100 kilohertz means how much is the on time and how much is the off time of 100 kilohertz, so that we can think of designing the, or we can think of putting the values in the timer. Okay, then also listen to me. Your clock frequency is 22 megahertz. Machine cycle frequency is what? That 22 megahertz divided by 12. How much? 1.833 megahertz. Okay. And machine cycle time, how much it is? 0.546. How? 1 divided by machine cycle frequency, 0.546 microsecond. Okay, now what do we have to generate? It's okay, this is the frequency given to us. We have to generate 100 kilohertz. What do you mean by 100 kilohertz? In terms of time, 1 divided by 100 kilohertz means 10 microsecond. Total period of 10 microsecond. On for 5 microsecond, off for 5 microsecond. Right? That we have to generate. So how much delay we have to generate in this case? We have to generate the delay of 5 microsecond. Is it right? So This we have to do. For generating the delay of 5 microsecond, now look here, one machine cycle time is 0.546, and how much we have to generate? 5 microsecond. So how many machine cycles will be required? 5 microsecond divided by 0.546 microsecond. Look here, 5 microsecond divided by 0.546 microsecond means 9 is the value coming out to be here. Okay, either we can go for hexadecimal. Okay, we can go for hexadecimal, or in decimal we can subtract it from 65536 minus n. It becomes how much? 9 we are subtracting, so 65527. In decimal, convert it to hex, it becomes FFF7. This we have to feed to the timer. We have to start the timer, and timer will go on counting and reach to FFFF. So when it reaches to FFFF, it will give us the delay of how much? 5 microsecond, which is required on the particular pin. After that, the pin will go low. Okay, it was high, giving you the um, half part of what? This 100 kilohertz. Then it will go low and remain low for again 5 microsecond, giving you the remaining half cycle of that frequency. That is how we are solving the problem. Okay? I think we will stop here, but it is required that you people are responding and trying to solve the things. Yes, may I stop here? Okay. Yes, I'm completing it because I think